Hi, my name is Pallavi Batula, and this is my Lab 5, the Slinky Drop. So the purpose of this lab is to choose something physics related that we're interested in, and for my experiment, we're observing the Slinky Drop. We are observing that the forces like tension and gravity are acting on different parts of the object during free fall. That goes hand in hand with our goal where we're attempting to understand the forces that are transmitted in a material. The result that we saw is that the bottom end of the slinky appears to hover in midair before its collision with the top half of the slinky. I used the video to gather my initial conditions and as well as using GlowScript to build a computational model. So fundamental principles that I used were Newton's second law, where the system's change in momentum is proportional to the net force applied. I also learned about tension and force transmission, where basically tension within the slinky balances the weight of the lower coils until the wave release reaches them. Think about it like F net, where tension is the upward force and gravity is the downward force. And now moving on to gravity, that provides a constant downward force driving the motion. And we can't forget spring force, which is Hooke's law, which states that the force exerted by the spring is proportional to its extension or compression. So this was the video that was the backbone for modeling the computational model, or rather, an attempt at building it. These are the 4 important clips from the fall of the slinky that I truly base off of. And since I wasn't able to use Tracker due to software issues, I set approximate initial conditions where the height was around 5.5 meters, the mass was around 0.02 kilograms, and the initial velocity was 0 meters per second because it starts from rest. And now on to the computational model. So these are my initial conditions. So the slinky is modeled as 20 small masses connected by springs. That's why n equals 20. And think about it like each part of the slinky is dropping down to the bottom half. And the mass of each segment is 0.02 kgs, and that represents the small portion of the slinky, and they're represented as spheres in the result. I also have the spring constant, which is 100 Newton meters, and I have the rest length of the spring of each spring segment, which is around 0.1 meter. I have the gravity vector, and I have the ground level because I really wanted to include that the slinky is dropping onto the ground. So this is our calculation loop. Is running frame by frame, and it continues until t equals 5 seconds. And in the simulation loop, what they're doing is they're modeling the slinky first being held in place for 1 second, and then you drop it. And during that, we allow gravity to kick in and start pulling all the masses down, and that's what the calculation loop is doing. And instead of falling at once, we are trying to be very particular in our computational model. So each mass feels forces from the spring connecting to the ones above and below, just like how it could be in the slinky. And so behind the scenes, we, of course, update the forces and the velocities and the positions little by little, just like how we do it in any regular lab simulation that we've done in the past. So this is the result that we got. So when the simulation begins, the slinky is at equilibrium with each mass position below the previous one, and it's connected by springs, like I said before. Basically, gravity pulls it downwards, and it initiates a wave-like motion that propagates through the slinky as the spring force acts on each mass. And the lower masses don't move immediately, and they wait till the top masses hit them before moving down. So this is some key comparisons from the models from both observed and computational. I definitely didn't use a spring in my computational model because I wanted to model the forces that act upon the slinky on the top and bottom parts. And the computational model doesn't seem so natural, and it only really highlights 2 technical points, whereas the observed model is just a straightforward free possible errors. So I could have a completely incorrect perspective when approaching this computational model. And second, I could have had a incorrect spring force calculation, and I could have not accounted for the actual magnitude of the tension and gravity. So now let's ask ourselves a what if question. What if the spring constant was increased or decreased? If the spring constant was increased, the slinky would itself become stiffer, and it would cause the masses to oscillate more rapidly when the top mass is released. Now, if it was decrease, the slinky would be more elastic and the system would take longer to settle to its final position. Now, our main question is, does the bottom of the slinky stay stationary just like in the video? And it does not, and here's why. In the In the model, the bottom mass is assumed to stop moving once it reaches ground level without replicating the natural behavior of the slinky bouncing through the surface. Now, unlike the video, the model doesn't simulate the wave reaching to the bottom and reflecting or interacting with the environment. So the model lacks these two dynamic interactions that are very important. So thank you so much for listening. This lab definitely was a stepping point when creating computational physical models. It wasn't perfect, but I definitely learned a lot on how to lay observed motion onto computer science. Thank you.